Hi, Nihit. Welcome to Scientific Dialogue. Thank you so much for taking out the time. So today we'll be talking about Nihit's, journey doing a PhD. What inspired her to get into science in the first place, and why did she end up, doing a PhD, and why is she choosing to work in the industry and not in academia? So, questions like that. So maybe Nihit, we can start from your introduction.
Hello, my name is Nihit Pokhrel. I'm an applied scientist at Microsoft. Um, my journey has been different than many, I would say, in that, a lot of folks end up in academic research after their PhD, but I got my PhD in computational chemistry, and we'll talk about what computational chemistry is in a little bit. After that, I went on to being an architect, a solutions architect at Amazon Web Services, AWS. And from there on, I started exploring the field of cloud computing and what cloud computing can do for science, and which then led me to my current job as a scientist at Microsoft, particularly at Azure Quantum. And you asked a great question, why academia versus industry? Quite honestly, I actually, when I graduated, I knew that I was not interested in a career path in the academia. I did not know what exactly I would do in industry. I knew that I did not want to be a postdoc. I did not want to be a professor. But in the industry, I was open to many roles. Particularly, my research was in simulating drug molecules. So I actually had thought that I would be in a big pharma company running chemistry simulations, discovering and finding out drug molecules. So it is actually quite an accident, I would say, by which I landed at AWS and then now I'm at Microsoft.
Got it. But why did you choose computational chemistry? You could have chosen any of the other scientific topics. Why computational chemistry?
A great question. So, computational chemistry is a branch of chemistry where you simulate chemistry, really. Think of reactions. So, doing reactions in lab versus what I do is doing reactions in a computer. And so, why I chose that was twofold. First, you could really get to the interactions at microscopic level, which experimentally you can see. So, we all have microscopes, we all can see things in detail, but the detail that computational analysis gives us, you could actually see things move real time and do the analysis and really pinpoint what chemistry is important when you do it on a computer versus when you do it in a lab. So that was one fold. And second fold was the time to do reactions is generally long. So, you have to think about the chemistry that's happening. You have to design the reaction. You have to go to a lab that has the right set of instruments that would give you the reaction mechanism in detail versus on a computer it was a pretty much a low barrier. You have to install a couple of software, and you all you really need is one or two powerful computers, and you could just study the same thing on your computer or an HPC, meaning high performance compute cluster, where you submit jobs and you get good results out of the simulation as opposed to doing the experiment.
But Nihit, maybe you can talk a bit about why do we need simulations? Like, what value can we derive out of that, or is it just a scientist, having access to a supercomputer, just trying stuff out? What value can we drive, and why would an industry be interested in simulating chemicals? Maybe for an 18-year-old who's watching this, why should they be interested in something?
Yeah, that's another great question. So computational chemistry up until some years ago used to be um, mechanistic, meaning if you do not have enough information from a lab, you would simulate something to explain why things happen. For example, if you realize a protein would bind to a membrane, what you would use computers is to explain why that protein might bind to a membrane. That was a long time ago. But now the field has changed so much that instead of explaining things, computers can be predictive with AI and ML, right? So what really now is it's actually a really great shift in how we do chemistry. So instead of just explaining what might happen in lab, now we can come up with new molecules and perhaps switch the direction of how research is done. So you have now with generative AI, you can make new molecules and then study that molecule and figure out what the molecule might behave like and then go to your experimental collaborators and say, hey, I think this molecule would be really cool for, drug discovery. And then they in lab can synthesize what you found on a computer and therefore can come up with a new molecule that they wouldn't have thought of before.
Got it. So I'm expecting to derive true value out of studying computational chemistry. You need to be able to work in an interdisciplinary team. Maybe you need to also work with a biologist. Maybe you also need to work with the pharmaceuticals industry. So to derive true value out of the whole process, right? When was the time in your academic journey while you were studying that you decided that you wanted to get into computational chemistry, and what were the other options you were considering at that time?
Yeah, so I went to an undergrad school which was, relatively small. And so I got my undergrad in math and chemistry. So I have bachelor's in both math and chemistry. And when I was in my third year undergrad, I started thinking about, okay, so how do I put these two things together? I like math. I also like chemistry. And I also figured that I was a little clumsy in the lab. So I thought, okay, what is the best way to put these two together? And then in my summer of my third year, I had done an internship in Germany also, where I really got to use computational tools for the first time. And it was really a game changing experience for me because I really, for the first time ever, I actually put, some of my programming skills, some of my statistical mechanics, some chemistry all together to see the power of computational chemistry. So after that, when I applied for PhD programs, which happens in fourth year of grad school, I had applied to universities with good computational chemistry division, and therefore I ended up being a computational chemist.
What were your inspirations at that time?
Yeah, so my inspiration at that time really was to work in a pharmaceutical company and bring drugs to market fast. That was what I was after. And, I had read somewhere that drugs to market, it takes about $10 billion to bring one drug molecule to market. $10 billion in 10 years was the timeline and the cost associated with it. And I just thought, wow, if I could do a little bit from my end to reduce this cost and time, it could be so useful to the entire world. So that was my basic motivation. And I actually then worked backwards and figured out, okay, so based on my interest in chemistry, what is that I can do and how can I maybe nudge this field just a little bit?
So what sort of open questions are there in your field right now?
Yeah, so there is many open questions. I talked about drug discovery because that happens to be my field of expertise, but there is, paints, figuring out um, what chemicals should be in paint so that paint does not corrode easily, right? So, and that really is an important question for so many of us because, making better materials is always a priority. Battery, for example, how to make better batteries, right? And, how to make better conducting materials. Even if we say better, that actually really means that you have to define the scientific problem. So this chemistry and computational chemistry particularly has so many open questions. You can pretty much think about, your computer right now, right? So what type of material to use on your computer to make the computer lighter, for example. So these all
Mhm,
down to chemistry problems. And so
mhm.
those things, and particularly for me, the kind of questions I was considering is, energetics related to drug discovery. So, how much energy would be needed for you to get sick, for example, or the vice versa is what I was actually doing is that, okay, say if I am sick, now I have a drug molecule. Will this drug molecule be efficient enough to cure me? That's the kind of question that I was working on.
I'm curious to know what would a day in your life look like.
When I was doing simulations, I was explaining the mechanism. So I was not trying to come up with anything new. I was trying to explain why one type of peptide is a part of protein, would attach to your cell membrane. That's the kind of research I was doing. And I was really after, how much energy is needed. Does it depend on what the composition of your cell membrane is? Meaning, if it's positively charged, if it's negatively charged, does it need to have ton of water? What about pH and mechanistic chemistry questions like that?
When you were growing up, were you always interested in math and chemistry, or did you develop that interest later on in your journey?
I liked math. I also enjoyed chemistry. So I remember when I was in high school being very fond of solving organic reactions. And somehow it would just come naturally to me. So I would know, what reacts with what and gives what. And so I remember helping my friends with their homeworks because it was just easy to me while others found it harder. Math also the same. I wouldn't say pure math, but I really enjoy statistics. The questions like what's the probability of raining tomorrow given it rained yesterday and questions like that. I really enjoyed solving that. But I didn't know that, this is what I would end up doing.
Do you feel that there's an imbalance in terms of how many people go into, let's say, physics or engineering versus how many people go into chemistry? Why is it so disproportionate? And do you think is it because uh, you know uh, while growing up we are taught that I think it's more of a PR problem for chemistry. Chemistry isn't sold enough in schools, and with physics and engineering talk about how the world works. How do you engineer things? You work with stuff hands on more. I feel, and maybe in developing countries it's more. What are your thoughts on this?
Yes, and the line actually in my mind is really blurred right now. Chemistry, chemical engineering, physics, biology, math, applied math is all blur. At least the in my field, I cannot consider, for example, people I work with have PhDs in physics, for example. So we all work very closely, but you're right. Growing up, I would actually say, pure science in general was not fun because we were said, okay, solve Newton's equation of motion to figure out how much velocity the ball will bounce back by. But I think the problem was that bigger picture was not clear.
Got it. I think, yeah, I think most people would be like, teach me real stuff, teach me quantum mechanics. I don't want to study Newtonian mechanics.
Exactly. And so even math, right? I remember thinking, when would I need these crazy trig functions? Why would I need to memorize all of this? But had we known the big picture and what the application is, I think it would be very different. And another thing to give some credit to where we come from. I'm originally from Nepal, so I don't know what anybody would a degree in chemistry do in Nepal even today.
Yeah.
So even from job perspective, you have to be an engineer if you're in the scientific field, right? So if you get a degree in chemistry or biology, what would you do? I think that's still a question that exists there. And, people like us who are fortunate enough to not um, be, pigeonholed as a chemist, and now we have the expertise and an interest in working in tech, as well as talking to customers, trying to figure out what the industry is doing. All those things, I think, will hopefully slowly change the direction of what chemistry really means as a career.
Nate, you mentioned earlier that it became very clear to you that you wanted to go into industrial research and not into academia. Uh, can you talk more about how did, like, what was the thought process going on in your mind, and how did you come up with this decision?
So the thought process at that point for me was how competitive a career in academia was and how many positions were open.
Hmm.
You know,
From a
and
supply and demand perspective.
that's correct because a lot of smart people around me, everybody wanted to be a academic person, and that translated to me as to there's a lot of competition. There's not many jobs because the end goal is to be a professor. Is it is it realistic? I love this field. I enjoy this field, but is this the only way I could contribute to the field?
Hmm.
And then I think I am lucky in that I live in Seattle, Washington, in America,
Yeah.
which happens to be the headquarters for Amazon Web Services as well as Microsoft.
Hmm.
So the field, the tech field at that time, particularly cloud computing, was really interested in venturing into sciences. So, what
Hmm.
can cloud computing do for basic pure science? And
Hmm.
I got an opportunity to merge those two together.
And Nihit, now that you have spent quite a few years in in industry, do you feel it was the right decision? And how has your experience been so far?
Oh yeah, absolutely. I love the work that I have done in the last 4 years. I'm glad. I if I sometimes think about what would the career in academia be like. If I was in academia, I'd probably be a postdoc somewhere, trying to find my path to become a professor.
Yeah.
It's been fun in terms of where my career is, as well as to see maybe not prioritize the research as much, rather see the big picture in that, what can technology do for science? I think that is where I got the most excited when I first joined industry.
Since you're living in Seattle, uh, what do you think is the big tech interested in right now? What areas of science is it most interested in, and why so?
Oh, this is a great question. And I think the answer is quite simple right now is the application of artificial intelligence and machine learning
Yeah.
in solving biology.
Nate, can we dive deep into the protein folding problem? I really want to learn more about it.
So amino acids are the building blocks for proteins, right? So amino
Yeah.
acids make a protein, and the challenge there is the structure of protein really depends on the amino acid and how they are connected to each other. And they fold sometimes, they unfold sometimes. That capturing that is very difficult. And so
Hmm.
therefore the model, lots of new models are coming which predicts how two, three, four hundreds of amino acid can come together because they can take different types of structures. And so what is that structure? Where does that structure come from? What's the most stable structure? Those are the challenges.
Got it. Got it. And how do you see this field progressing maybe 5 to 7 years from now? Apart from the fact that, with AI, we would be able to push this a lot. But, what other technologies are there, such as maybe you can talk a bit more about quantum computing, for example. How would these technologies help us make progress in this field?
Yeah, so simulation will be faster just with high performance compute, right? So we have big clusters now. What used to take, a couple of weeks, now we can simulate relatively easily. So with the advances in computing, high performance compute, cloud compute, we can simulate all these things faster, better, and reiterate quickly.
Nihit, how was your experience doing PhD? Because it's like 4 or 5 years of hard work. What sort of ups and downs were there in that journey?
Yeah, and I think it'll be true for most of us when I say there is a lot of ups and downs, particularly, people who end up going to do their PhD were generally, top of their class, really dedicated to the science and want to do the science. So the first year was not much different from undergrad. So the way the PhD, I went directly from my undergrad. I didn't get a master's, so I got an undergrad and then I went to my PhD. First year was more or less the same, where we all sat together and then do our homework, take classes, try to help each other, try to figure out what kind of research you want to be in. That was pretty much the same as my undergrad. The second year was perhaps the most exciting year for me because that's when I was first thrown into independent research. I was learning a lot about my field, reading tons of paper, starting to do, my own independent research. And then third and probably the fourth year was the most difficult year for me because at that time it felt like it's very difficult coming up with new things and actually proving that what my hypothesis is actually true. Fourth year was really difficult. That is when, I also spoke to some of my friends. All of us thought, wow, this is quite difficult. It's not a smooth sailing. There's a lot of, I don't know, I cannot prove it. Don't, there's no paper that has done it before. So then it was just you and your academic advisor driving the field of science altogether, right? So you then become the expert in this field. And so then you are single handedly pushing the field.
An 18-year-old watching this, how should they, start developing their interest in this field? Where should they actually start?
First of all, just be aware of the field. Computational chemistry, I don't think actually comes up for a 18-year-old ever, right? So in classes, I don't think computational chemistry is even talked about. So
Hmm.
just a good spot is, Google and say what are the branches and what fields are there in chemistry? Because when we, at least for me, that was true when I was growing up. I thought chemistry was pretty much just organic chemistry. I
Hmm.
didn't know beyond that. And so and not for chemistry, I think this is true for any scientific field. We just bucket them in one big chunk, but it's so different. From
Hmm.
example, physics, right? There can be so many branches of physics. Your physics can be close to biology, can be close to chemistry, can be close to math, can be close to space, can be close to stars. So figure out what is that you're interested in, and then see if there's a branch of
Hmm.
physics that exists or chemistry that exists. That's the very first stop, I would say. Second stop is that you have to be good at math. And if you're good at math, also ask the question, if you are interested in applying math to a problem that may not look like math. For example, what is drug molecules doing does not sound like a math problem, but behind the scene, it's truly math. You're just solving equations of motion.
Hmm.
And so it truly is a math problem that you're solving in a different context.
But what sort of math are you talking about? Because there are a lot of areas, right? There's calculus as well. There's probability and statistics as well. What areas of math are you particularly talking about?
All, I would say, all, because you have to be able to do some data analysis. Statistics definitely comes in. You have to
Hmm.
be able to talk about averages. Again, statistics comes in. You have to be able to propagate things as a function of time, which is
Hmm.
differential equation.
Hmm.
Uh,
Hmm. Hmm.
all, everything really. You have to be able to solve for a variable. So algebra definitely, right?
Hmm.
So
Hmm.
there's a and so, if you're curious in math and you want to apply the field of math, um, then I think computational chemistry is a really good field to be in.
Maybe towards the end, I do want to ask about when you were applying to, different companies after your graduation, what sort of questions were you asking yourself? Maybe this is the company culture that I want for myself. These are the people that I want to work with. So what were the questions coming up in your brain?
That's another great question. Yeah. So for me, it was, can I use my expertise? Will I let my PhD go if I would go to a tech company? Right? Will I use the knowledge that I have gathered in the last 8, 9 years of my academic career to do something relevant? That was question number one. Question number two was, what's the work-life balance, right?
Hmm.
So does it presumably you will be paid more because industry tends to pay more than academia, but does that mean that I will not have a life outside? Does, that. And then third thing is, what are the people who are in the team? And that's really important because then that helps you learn, right? So as someone who was taking up industrial job for the first time, it was really important for me to learn because this was my first ever job outside of academia. So
Hmm.
I wanted to learn as much as I could. And when I say learn, I mean learn about business. How's the business done? Uh,
Hmm.
how do I, advertise myself? How do I
Hmm.
talk about how the field can benefit from the high performance compute at that time, right? So
Hmm.
these are the things that I was really asking while I was trying to get a job.
Very interesting. Thank you so much for sharing that insight. Last question from my side. So, how do you make your presence felt in the industrial space? So, you talked about how there's a lot of competition in the academic world, but I'm pretty sure that a lot of people would love to also work in research positions at big tech as well. So, how do you make your mark, and what are these employers at these companies looking for? And in people who are coming directly out of a PhD program.
Most importantly, just someone who can learn things. And I think that's what our PhD training trains us, right? It makes you comfortable with the uncomfortable. So that's the thing they want to see, that you don't know anything, that's fine, but you have the ability to learn things quickly.
Hmm. Yeah,
And
but that also requires trusting the process that you're gonna be okay after a few months.
right, and it's not just them, you yourself, right? As academics, we are quite known to be perfectionists. We have to know everything in the field, but being okay not knowing everything and then saying it loud that I don't know, I'll learn it is actually, for me it was very difficult because my academic mindset said, no, you have to know it all. There's no saying I don't know for the longest time. But eventually I learned saying, okay, I don't know, but I can look it up. Let me ask around.
Hmm.
So
And
those
then saying I don't know requires courage.
exactly, and it's really a learning curve. It was a learning curve for me. I still, struggle when I have to say I don't know, but it's okay. Nobody reprimands you for saying I don't know. So
Hmm.
that's quite a fresh air. If it's a question about your field, I think the expectation is still that right? So the if you're talking about what your PhD was, and if I say I don't know, I will look bad wherever it is. But
Hmm.
things that are outside my academic research, it's okay to say I don't know in both spots, but we generally only see people talk about their area of expertise in academia. So I
Hmm.
think is the that's why we don't see a lot of people say I don't know, not because it's frowned upon, but because you only experts talk about the field. Non-experts do not talk about the field. And I think that is the shift or the difference in academic world versus industrial world.
Got it. Thank you so much, Nihit. This was a very insightful episode. I think it's a great introduction to working in industry versus academia, and also talked talked very eloquently about drug discovery as well. So thank you so much for sharing that insight. Really appreciate it.
Of course, thank you.